Hello and welcome to Lecture 4 of Chemistry for the Interdisciplinary Sciences. Today we're going to be having a look at the number of atoms that need to react together. So we're going to look at chemical formulae and also look at ratios and how it is that a chemist puts together the right masses of two compounds to ensure that there is a complete clean reaction. So let's have a quick glance at the learning outcomes. Today we're going to understand the term stoichiometry. We're going to use chemical formulae and we're going to balance equations. We're going to look again at how you figure out what the chemical formula of a substance is. And then we're going to look at the term mole and start thinking about concepts describing how strong a solution is or how much of a substance you have. So let's start with stoichiometry. Stoichiometry is the calculation of the relative ratios of the number of molecules or compounds that you need to react together. So by that, what I mean is, if we have a look at this this model here, what is drawn, we've got hydrogen molecules and oxygen molecules. I'm just going to get rid of that pen. And the hydrogen molecule here is made up of two hydrogen atoms, and the oxygen molecule is made up of two oxygen atoms. When we do the reaction, they break their bonds, they change partners, to make a water molecule whose formula is H2O. We're going to find out how we can tell that in the next couple of lectures, but for now I'm sure you're aware that water has the chemical formula H2O. That being the case, notice that we have two hydrogen atoms on the left hand side of this arrow, and we have two on the right, which is great, but we have two oxygens on the left hand side of this arrow, and only one on the right hand side. And if we look at the equation, we can see that a little bit more clearly. Hydrogen 2, two hydrogens, two oxygens, only the one oxygen here because there's no number after it. That means that in this equation we're suggesting that the oxygen atom just disappears into thin air, which just can't happen. So instead what we have to do is look at, well, if we've got one more oxygen atom, we're going to need two more hydrogens in order to make another water molecule. So we can change the stoichiometry of the reaction. We can change how many hydrogen molecules we have per oxygen molecule. And a quick reminder, this is an oxygen molecule because there is more than one atom bound together. Okay, so if we correct that, we put two hydrogen molecules in there. So now if we count them, we got four hydrogens there, two oxygens there, two oxygens there. So far, so good. Everything is balanced. How do we write that as an equation? Well, we use the large numbers in front. So no matter what the reaction, hydrogen is H2. And you'll see why in the next lecture. It's because hydrogen only needs to make one covalent bond. So these hydrogen atoms can't attach to anything else. They are stuck exactly as they are. So the small numbers here are used to describe compounds no matter what the reaction is. Those compounds are those compounds with those exact ratios of atoms in them. The large numbers describe this reaction when hydrogen and oxygen come together. So now we're talking about dependency rather than hydrogen on its own hangs out as H2, no matter where it is, no matter what situation. The large number here, the 2, means that we must have two hydrogen molecules. So there we can see the molecules, two of those hydrogens, separate molecules, so they are H2s, and there are two of them. Over here, two water molecules, again, two separate molecules, which each have the equation H2O, two hydrogens and an oxygen. Let's have a go at balancing the next one. So let's say we have aluminium and chlorine reacting. And just for fun, let's have a quick look at what that looks like when they react. So I'm going to pop this on here. So yeah, yet again we have interesting Spanish music. Just going to turn that down. Okay, so here we have chlorine as a gas. Really, really nice. Chlorine is a green gas as it goes. We're heating up some foil to give it a little bit of activation energy. And there we see the aluminium starting to react. We're seeing a change in colour. And now we're seeing energy being given out during this reaction. So what we're hoping to see is that the chlorine has reacted in some way. We're not expecting to see that green gas anymore at the end. And it seems like we don't. We've just got a whole load of smoke, presumably in there, which is probably aluminium reacting with some of the oxygen. So there we can see the balanced equation. Now let's see if we can get there ourselves. So the first thing to do is say, okay, aluminium. When we have aluminium, it bonds only to itself, so it's an element on its own. Now, we're going to see that a little bit more in the metals lecture, which is all the way in lecture 8. So don't worry if you're not sure why aluminium, when it's elemental, is just Al all on its own. And we're also going to see why chlorine is Cl2 all on its own in the next lecture. So don't worry about being able to write those, but we should be able to figure out, now that we've looked at the ionic reactions, aluminium chloride. So why is it AlCl3? Again, it doesn't matter what reaction it comes from, aluminium chloride will always have the same formula. Well, here it says that aluminium is an Al3 plus ion. Does that make sense? Well, if we pop to the periodic table, we can see aluminium in the 3p1 position. So the first element along in the p block there on the third row. So that means that it wants to lose 3 electrons in order to complete its shell there. So aluminium is going to be a 3 plus ion. Now chlorides are written as a Cl1 minus. Does that make sense? Let's go to the periodic table again. Chlorine is there in the 3p5 position, so proton number 17. It's in group 7. So being in group 7, that means it has 7 electrons in its outer shell. It wants 1 more electron. And so having that 1 more electron means that we're going to have just a single minus, 1 more electron than we have the protons in there. So finally, we need to balance charge. We need to make sure that there's a minus for every plus. That means that we must need 3 chloride ions for every 1 aluminium ion there. Okay, so that being the case then, we need to think about the fact that we've got AlCl3 and our chlorides come in 2s. So if we get our chlorine atoms in 2s and they're going to get bunched into 3s, then I can think about what is the most common multiple of those two numbers. For the aluminium, it doesn't matter. If we had 20 molecules of aluminium chloride, then I just put a 20 in front of the aluminium. That's not a problem. But if the chlorines come in 3s and we get them in 2s, then it must be 6. We're going to need 6 chlorine atoms to divide up correctly between the two. So how do we get 6 chlorine atoms on both sides? Well, we're going to say that we got 3 Cl2s, and then we're going to have 2 aluminium chlorides there. So again, the big number is saying, in this reaction, what are the ratios? Finally, the fact that we have 2 aluminium chloride molecules over there means that we must therefore need 2 aluminium atoms in the first place to be incorporated over there. So hopefully that makes sense. Now, you don't have to do it in that sort of mental process that we've got there where you're like making reasoning about the chlorides. You can use something called the roster method. And so that's what I'm going to try and do here. But we all know that handwriting on slides for me is a bit of a challenge. So let's give it a go. What I like to do in the roster method is I draw a line here between the products, the things that are made over there on the right hand side, and the reactants. Then what I do is I write a little list of how many atoms I have of each form. So I've got of each element. Hydrogen, I've got sulfur, and I've got oxygen. And what I'm going to do is, as I balance this, I'm going to keep that updated. On the right-hand side, I draw exactly the same thing again. And I do them in the same order so I don't get confused. And an O. Okay. So as written, how many iron atoms do I have on this side? Well, there's no number in front or after it, so I just have 1 iron atom. On this side, how many iron atoms? I've got Fe2 there, I've got no number in front of it, so that's just 2 iron atoms there. Let's have a look at the hydrogen atoms. On this side, I have H2, so that's just 2 hydrogen atoms, there's no number in front of it. And on this side over here, yeah, I have H2 again. So far, so good. Okay, how about sulfur atoms? On this side, I've only got the 1 sulfur atom. So I'm just going to write 1 there. And on this side, sulfur atoms. Now, I've got 1, but it's in a bracket with a 3 after it. So that means that there are 3 lots of the SO4 ion. And that means that I have 3 sulfurs. 3. Okay, finally my oxygens. Over on this side, I have 4 because it says SO4, and again, no number in front of it. And over on this side, I've got SO4, 3. So I've got 3 lots of the SO4 ion is a total of 12. There we go, 12. Okay, so now when I'm balancing the reaction, I've got a few little rules that I like to use in my own head that just makes this a lot quicker. Anything that is elemental, so what I mean by that is an equation that has only one type of elemental symbol in it. So in this case, that's iron and hydrogen. I'm going to leave those to last. The reason I'm going to do that is because I can change the number in front of them without messing everything else up. So that's my first rule. I'll leave my elements to the end. My next rule is that I'm basically going to try and balance the biggest disparity first. So in this case, that is the fact that I've got 12 oxygens on the right-hand side and only 4 on the left-hand side. So if I've got 4 on the left-hand side and 12 on the other side, then I can already see that I'm going to need 3 of these. So if I have 3 H2SO4s, then I'm going to have 12 oxygen atoms. Now that I've made that change, I need to update my entire roster. I like to cross everything out and just start again while we're starting out. And then eventually we'll just be like, okay, I can see that that's not changed. So how many ions? Still 1, nothing's happened to that. How many hydrogens? I've got 3 lots of H2 is 6 hydrogens. I now have 3 S's, 3 sulfurs. And I designed this to have 12 oxygens, so 3 lots of O4 is 12. Lovely. Okay, so oxygen's balanced now. Let's have a look at the others. What else isn't balanced? In that process, I accidentally balanced the sulfur, which is great. I don't need to change anything at all here. So now I look at my next biggest disparity, and I'm now down to the elements, which is great. It makes life a lot easier this way. So hydrogens, I've got 6 on the left-hand side and only 2 on the right-hand side. So to make it such that I have 6 on the right-hand side, or a better way to say that is to show how those 6 hydrogens have rearranged in the products, I'm going to put a 3 in front of this H2. Now again, usually I would cross all this out, and so I am going to do that at the start, even though we can see it's going to be all the same. So how many ions? Still 2, Fe2. How many hydrogens? I've got 3 lots of H2 is 6. How many sulfurs? Still 3 lots of SO4, so still 3. And how many oxygens? Still 3 lots of SO4, so that's 12 in total. Great, so the last thing that's not balanced is my iron. I've got 2 on the right-hand side, so I have to provide 2 hydrogen atoms in the first place. So all I'm going to do is put a 2 there. And again, I could update the whole roster, but I'm not going to in this case. Again, I would really encourage you to cross it all out and just check through every single time. What I suggest you do not do, a tip that I see students doing all the time, is adding. So let's say you did 3 H2SO4, they'd say, okay, 3 means 2 more, so I'm just going to think of it as adding 2. That does not work until you're very, very sure of the principles. So I suggest that you don't ever just try and add the atoms that you've drawn, cross them out and start again every single time. I don't mean cross all of them out, I mean cross out the elements that you use, that you've changed. I've seen so many people make so many mistakes just by going in their head, okay, I got 3, so now I've got 3 more sulfurs, and you haven't. You've only got 2 more sulfurs because you already had 1 in the first place. So that's where that error comes in. Please try and just cross them out and recount them every single time. Eventually you'll get so good at it that you don't need to write any of this at all anymore. So there are lots more examples of those in the balancing equation folder, and I also go through a few more just to make sure that it makes sense to us. So finally, now that I know that I'm going to need 2 iron atoms with 3 sulfuric acid molecules to make 1 iron sulfate molecule and 3 hydrogen molecules, I now might start trying to actually put those together in the lab. Now the problem is that I can't just count atoms because they're really, really small. So if you have a look at 1 atomic mass unit, so far you remember we said that a proton has a mass of 1. Well, what that actually means is that it relative to each other, hydrogen atoms, sorry, I'm just changing my pointer, hydrogen atoms weigh 1/16 of an oxygen atom. So these relative mass units are basically telling us what the weight of each atom is in comparison to each other. But in fact, a hydrogen atom on its own weighs 1.66 times 10 to the minus 27 kilograms. Now again, if we go right back up to that, this equation here where I'm saying I need 2 hydrogen atoms for every 1 oxygen atom, if I were trying to weigh that out, I would have to weigh out 1.66 times 10 to the minus 27 kilograms of hydrogen, and then twice as many as this. So what's that? 5.32 brain times 10 to the minus 26 kilograms of oxygen. You can see that that's going to be almost impossible. And once we get them all together, there we go. Oh my goodness, I did that maths in my head even though it was already on the slide. My goodness. So clearly that's not going to be possible. It's not going to be possible for us to start weighing out individual atoms. And instead what we're going to do is use a concept called the mole. So what is a mole? If I have just 1,000 of these molecules, you can see that this is still a ridiculous weight to weigh out. So 1.6 times 10 to the minus 24 is 0.00000 and so on. 23 noughts, and then finally get 1605. So that's not going to be measurable to us. What if we had a trillion, I think I've got there? Well, that's still times 10 to the minus 18. So again, that's 0 and then 17 noughts and then 166. So that's no good. And even if I have 1,000 times more than that, the number is still very small. So I'm going to have some gigantic number of atoms in order for it to actually be weighable to me. And so, because we're going to be arbitrary about that, we're going to have some number of atoms. Why don't we just count how many atoms it takes to weigh out 1 gram? So if we took this number on the periodic table, the mass number of the atom, and we just said, okay, how many atoms does it take to give me 1 gram? We come to the mole. Now, that number is not going to be the same every single time for every element. Let's say that I wanted a kilogram of apples and a kilogram of strawberries. Well, I did actually go do this because I'm a sad man. And what I found was that we had 4 apples in a kilogram, but 23 strawberries. So it can't be the case when I'm doing a reaction that I weigh out 1 gram of hydrogen and 1 gram of oxygen and then pull them together and suggest that I've got the right ratio of atoms. I'm not going to. Because oxygen atoms weigh a lot more than hydrogen atoms. In this case, we've got hydrogens that are little tiny strawberries and oxygen atoms that are great big apples. If I want 1 strawberry per apple, well, in fact, I want 2 strawberries per apple, don't I? Because it's H2O. This analogy has got a bit ridiculous. If I wanted 2 strawberries per apple, then I can't just buy 2 kilograms of strawberries and 1 kilogram of apples. I've got to actually figure out what the weight of each strawberry is. So that leads us then to the mole. The mole is the number of atoms of, now technically it's the number of atoms of carbon-12 that you need to weigh 12 grams. But we can also think of it as the number of hydrogen atoms that I need to weigh 1 gram. And if we go to the periodic table and pick any element, so helium, I'd need a mole of helium atoms to make 4 grams, a mole of lithium atoms weighs 6.9 grams, and so on. So I'm reading the periodic table to tell me what the mass of a mole of atoms would be. Now, because the periodic table lists these values, I'm just going back up for a second, lists these values relative to each other, then if I have 1 mole of hydrogen atoms and 1 mole of oxygen atoms, I know that that mole of oxygen atoms will weigh 16 times as many as the hydrogen atoms, because that's what the mass unit means. Remember, the atoms are only made up of protons and neutrons, so it can't be some crazy number. It's got to be basically multiples of each other, because hydrogen is just 1 proton, oxygen is 8 protons and 8 neutrons, weighing 16 times as much as a hydrogen atom. So the mole then turns that relative mass into grams, i.e. if I have a mole of any atom on the periodic table, it will weigh exactly the same as its mass number. So again, If I pick mercury, right down there at the bottom of the D block, mercury, I need 200 grams of mercury in order to get 6.022 times 10 to the 23 molecules per mole. To give you an idea of what that is about as many grains of sand as there are on Earth in terms of magnitude. So it's a lot of atoms there. But if I have 6.022 times 10 to the 23 of anything, of any atom, I will have exactly the atomic mass weight of those atoms. This is one of our SI units, and by the way, over here, this is called Avogadro's constant. So you might see that around and about. And these are two separate pictures of Avogadro, though the top one does look like Joseph Priestley a bit. So this leads us to an idea of standard international units, SI units, concepts that can be fundamentally only described in one way. And so this brings us to each of the different units. So let's just quickly think about them. Time. If I want to measure time, the fundamental unit of time that we're going to use in science is the second. And that's it. That's all of the units. That's the very most fundamental unit that we can possibly use. If I wanted to describe speed, then I'd be thinking about using a distance, which we measure in meters over here, per second. But I'm still using those two separate units. So all measurements that we make in science can be fundamentally brought back down here to one of the SI units or some combination of the SI units. So we have seconds, we have meters, mass we measure in kilograms as standard, though in chemistry we tend to use grams more. But remember, a gram is just 1,000th of a kilogram. Intensity of light, that's the candela. So again, it's talking fundamentally about photons of light in there. Moles is our fundamental unit of how many of something do we have. And so you can have a mole of anything. In the workshop materials, I'll try and remember to include the mole of moles article from XKCD, which would basically be a planet of mole animals there. We got A, ampere, that is a unit of current. Oh, I hope that's right. We got K, Kelvin, that is the unit of temperature up there. And that's it. All of the units can be described as some combination of these. And so things like volts, for instance, are going to be talking about the units now. Yes, okay, that's enough of that for now. So this takes us to the mole then. Now, a mole's really interesting when it comes to gases. Remember, gases, the molecules are not touching each other at all as they float about. If you have a mole of a gas, approximately all gases, 1 mole occupies 24 decimeters cubed, 24 litres of space. So that's really useful. In terms of volumes of gases, you can just calculate the volumes. So you might be thinking, because you can't weigh a gas, you can actually convert from the volume itself there. Finally, if we know that a mole of atoms weighs the atomic mass number on the periodic table of that element, then we can start to figure out the molar mass of any substance. So the molar mass of a compound is equal to the sum of all of the atomic masses of the atoms in the molecule. So let's have a look at this molecule here, propane. We're about to meet that in the next lecture. But this molecule is made up of 3 carbon atoms and 8 hydrogen atoms in total. So if we're saying that a mass of a mole of these molecules will equal the mass of 3 moles of carbon atoms, add the mass of 8 moles of hydrogen atoms, and remember, mole is just a number. It's like saying dozen. If I had a dozen atoms, what would that weigh? This is mole, which is a much larger number than dozen, but just think of it as like dozen there, where dozen is 12 exactly, in case you're not aware. Okay, so we're figuring out the molar mass of propane. Then what we need to do is figure out what is the molar mass of each carbon atom. So first of all, we say, okay, there are 3 of these. So I've got C3H8. I need to know the molar mass of carbons, so I have a quick look at the periodic table. Carbon is there in the 2p2 position in group 4. It's got proton number 6. So I can see that the mass number there is 12. So, okay, I'm going to have, for a mole of these atoms, I'm going to have carbon 3 lots of 12. If we think about the units of this, I'm saying 12 grams per mole of atoms. I'm going to use mole to the minus 1. Sorry, that got a little bit lost there, so I'm just going to write it again. Grams per mole to the minus 1. That is exactly the same as writing grams per mole. So whichever you prefer. There. Okay, so our carbons are going to weigh 3 times 12. Our hydrogens here, I've got 8 of them. And what is the mass of hydrogen? Again, I'm popping to the periodic table. There it is in the 1s1 position. It's got a mass number of 1. Okay, so 8 lots of 1 gram per mole. Oh, lost my pointer. Yeah, 1 gram per mole. Sorry, again, the minus 1's got hidden in the box there. So 3 12s are 36 plus 8. So let's just make sure we're making that calculation clear. 36 plus 8 grams per mole is 44. My goodness, brain. 44 grams per mole. So what that means is, if I weigh out 44 grams of propane, then I will have a mole of propane molecules. Then I can go figure out if I needed, I don't know, 6 moles of oxygen to react with that. Then I'll go weigh out 6 lots of the oxygen MR. Oxygen 16, O2, as it hangs out, would be 32. So I have to do 6 lots of 32 and add those together. Hopefully that makes sense. Again, if you're not quite sure, pop over to the balancing equations section and there'll be a short video there doing a few examples and the answers are also available so you can have a look. Okay, thank you very much. See you in the next lecture.